Hold a single grain of sand at arm's length against the night sky. That tiny speck, smaller than a pinhead, is blocking your view of 10,000 entire galaxies. Not stars, galaxies. Each containing billions of suns, billions of worlds, billions of possible stories. The James Webb telescope just spent 12 hours staring at that grain of sand-sized patch of darkness, and what it found has shattered every assumption we had about how large, how old, and how impossibly crowded our universe actually is. You think you understand scale? You don't. None of us did. Until now. I want you to try something with me right now, wherever you are. If you can, hold up your hand. Extend your arm fully. Now, with your other hand, pick up something small. A pencil eraser, a button, a small pebble. Hold it at the end of your outstretched arm and close one eye. Look at the night sky through that tiny object. What you're blocking from your view in that impossibly small patch of darkness contains more galaxies than there are people in a large city. More stars than there are grains of sand on a beach. More worlds than every story ever told by every human who has ever lived. This is not poetry. This is not metaphor. This is mathematics. This is reality. And for most of human history, we had no idea. We looked up at the night sky and saw perhaps a few thousand stars with our naked eyes. We built telescopes and saw millions. We launched Hubble into space and saw billions. And then we built James Webb, and everything changed. Because what Webb revealed wasn't just more of what we expected. It was something entirely different. Something that broke our models. Something that forced us to reconsider not just how big the universe is, but how it came to be this way in the first place. Let me take you back to the beginning of this story. Not the beginning of the universe, though we'll get there. The beginning of our understanding. Or rather, our misunderstanding. For centuries, humanity has been trying to answer one fundamental question. How big is everything? The ancient Greeks thought the Earth was the center of a relatively small cosmos, with the stars painted on a sphere just beyond the planets. When Copernicus and Galileo shattered that illusion, we realized we were orbiting the sun, not the other way around. But even then, we thought our solar system might be the entire universe. It wasn't until the early 20th century that we discovered our sun was just one of billions in a much larger structure we call the Milky Way galaxy. And then came the truly staggering revelation. In the 1920s, Edwin Hubble, using what was then the most powerful telescope in the world, discovered that those fuzzy patches of light scattered across the sky weren't clouds of gas within our own galaxy. They were entire galaxies beyond our own, millions of light years away, complete island universes, each containing billions of stars. The cosmos suddenly became unimaginably larger, but we weren't done, not even close. As our telescopes improved, we kept finding more galaxies, farther away, older, dimmer. Each new generation of instruments pushed back the boundaries of the observable universe. And with each discovery, we had to revise our estimates upward. Not by small amounts, by factors of 10, of 100, of 1,000. The universe kept getting bigger, but there was a limit, we thought. A horizon beyond which we couldn't see, not because our telescopes weren't powerful enough, but because light itself hadn't had time to reach us yet. The universe is 13.8 billion years old, give or take. Light travels at a fixed speed, so there must be a boundary, a distance beyond which we simply cannot observe, because the light hasn't arrived yet. This is true, there is such a boundary. But here's where it gets strange, where our intuition completely fails us. That boundary isn't 13.8 billion light years away, it's much, much farther. Because while light has been traveling toward us, the universe itself has been expanding, space has been stretching. The galaxies that emitted the light we're seeing today were much closer when that light began its journey. But in the billions of years it took for those photons to reach us, space expanded, carrying those galaxies away, pushing them to distances far greater than light could have traveled in that time. The result is this: the observable universe, the bubble of space we can theoretically see, is not 13.8 billion light years in radius. It's 46.5 billion light-years. The diameter of the observable universe is 93 billion light-years across. Think about that for a moment. The universe is older than it is wide, in some strange, counterintuitive sense. Or rather, it's wider than its age would suggest if we forget that space itself is growing. This expansion is not galaxies moving through space, it's space itself expanding, carrying galaxies along with it like raisins in rising bread dough. This is perhaps one of the hardest concepts in cosmology to truly grasp. We're used to thinking of space as a fixed stage on which events unfold. But space is dynamic, it's stretching, and the farther away something is, the faster it's being carried away from us by that expansion. There are galaxies so distant that they're receding from us faster than the speed of light. Not because they're moving through space that fast, which would violate relativity, but because the space between us and them is expanding that rapidly. Now, I need you to understand something crucial before we go any further. Everything I've just described, this picture of an expanding universe filled with billions of galaxies, this was our understanding before James Webb. We thought we had the story mostly figured out. We had a timeline, a narrative. After the Big Bang, there was a period of rapid inflation. Then space expanded more slowly. Matter clumped together under gravity. The first stars formed a few 100 million years after the beginning. Those stars lived short, violent lives and exploded, scattering heavier elements into space. Those elements allowed the next generation of stars to form, along with planets. Galaxies assembled gradually over hundreds of millions of years through mergers and accretion. Black holes at the centers of galaxies grew slowly as material fell into them. Over billions of years, this process created the structured, organized, majestic cosmos we see today. It was a story of slow, steady, predictable evolution, from chaos to order, from simplicity to complexity. This story was beautiful. It was elegant. It was based on solid physics, on sophisticated computer simulations, on decades of observations from ground-based telescopes and from Hubble. We believed it. We taught it. We built our understanding of cosmic history on it. And then James Webb opened its eyes and looked deeper into the universe's past than we've ever looked before. And what it saw broke the story completely. Let me tell you what Webb found. But first I need to explain how Webb actually sees, because this is crucial to understanding why its discoveries are so revolutionary. The Hubble Space Telescope, magnificent as it was, observed primarily in visible light and ultraviolet, the same wavelengths our eyes see. But light from the most distant galaxies has been traveling for so long, through so much expanding space, that it's been stretched. The wavelengths have been pulled longer and longer, shifting from ultraviolet into visible light, from visible light into infrared, from near-infrared into mid-infrared. This is called redshift, and it's exactly analogous to the Doppler effect with sound. Just as an ambulance siren drops in pitch as it speeds away from you, light from receding galaxies shifts toward the red end of the spectrum. The most distant galaxies Hubble could see had their light shifted into the near-infrared, but the very first galaxies, the ones that formed just a few 100 million years after the Big Bang, were so distant, receding so quickly, that their light was shifted far into the infrared, completely beyond Hubble's range. These galaxies were invisible to Hubble, not because they were too dim, though they certainly were distant and faint, but because Hubble was looking in the wrong wavelengths. It was like trying to hear a dog whistle. The sound is there, but your ears aren't built to detect it. James Webb was specifically designed to see in infrared. Its mirror is covered in gold to better reflect infrared light. Its instruments are cooled to -233 degrees Celsius to prevent their own heat from overwhelming the faint infrared signals from distant galaxies. It sits not in orbit around Earth, but at a point in space called L2, 1,000,000 miles away, where it's shielded from the sun's heat by a tennis court-sized sunshield. Everything about Webb is optimized for one purpose: to see the most distant, most ancient, most redshifted light in the universe, to see the first galaxies, to witness cosmic dawn. And when it finally turned its gaze toward the deepest, darkest patches of sky, what it found was not what anyone expected. Let me take you to one galaxy in particular. Its designation is Jade's GS Z140. That string of letters and numbers is not a name, it's a coordinate and a measurement. The Z14 part tells you its redshift, which corresponds to how far back in time we're seeing it. And that number, 14, means this galaxy existed just 280 million years after the Big Bang. If the entire history of the universe were compressed into a single year, with the Big Bang occurring at the stroke of midnight on January 1st, this galaxy would have formed on January 7th. We're seeing it in the first week of cosmic time. Now, you might think, well, of course, the first galaxies were small and dim and primitive. They were babies. They hadn't had time to grow yet. But here's the thing that stunned astronomers. Jade's GS Z140 is not small. It's not dim. It's not primitive. It's massive. It's bright, shining with the light of hundreds of millions of stars. It's already forming stars at a furious rate, creating new suns faster than our Milky Way does today. And spectroscopic analysis shows it contains elements heavier than hydrogen and helium, which means previous generations of stars must have already lived and died by this point, enriching the gas with carbon, oxygen, and other elements. This galaxy should not exist, not in this form, not this early. According to our models, according to the simulations we'd run thousands of times on supercomputers, galaxies this massive and this bright shouldn't have been able to form for at least 500 million years, possibly longer. The universe simply didn't have enough time. After the Big Bang, matter was spread almost uniformly throughout space. Yes, there were tiny fluctuations, quantum variations in density from one region to another, and yes, those denser regions would have begun to collapse under their own gravity, pulling in surrounding matter. But this process takes time, a lot of time. Matter has to fall inward, it has to collide, it has to lose energy through radiation so it can settle into rotating disks. Then stars have to form from the densest regions of those disks. Those stars have to live out their lives. The massive ones, the short-lived ones, have to explode as supernovas, scattering heavy elements. Only then can the second generation of stars form, the ones that can create planets, the ones whose spectra show the presence of elements other than hydrogen and helium. This whole process, from the initial density fluctuations to a mature, actively star-forming galaxy, should take at least 500 million years. That was the minimum timeline. It was based on physics we understood. Gravity has a certain strength, gas clouds cool at a certain rate. Stars form according to well-understood processes. You can't rush it. Or so we thought. But Jade's GS Z140 exists, and it's not alone. James Webb has found hundreds of galaxies in this same early epoch, all of them too big, too bright, too mature, too fast. There's a term astronomers are using now, the impossible early galaxy problem. It's not that these galaxies are truly impossible, obviously they exist, we're looking at them, but they're impossible according to our models. Something is wrong with our understanding. We're missing a piece of the puzzle. Perhaps dark matter clumped together more efficiently in the early universe than we realized. Perhaps there were supermassive stars in the first generation, objects hundreds of times more massive than our sun, that could rapidly produce and disperse heavy elements. Perhaps the star formation process itself was different back then, faster and more efficient. We don't know. And that not knowing is both humbling and exhilarating. Because here's what this tells us. The universe doesn't follow our scripts. It doesn't wait for our permission. It doesn't care that our equations say this shouldn't happen yet. It does what it does. It is what it is. And all we can do is watch, measure, and try to understand. Let me tell you about another discovery that's equally baffling. This one involves black holes. Now, you've probably heard of black holes. Regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives, compressing all their mass into an infinitely small point called a singularity, surrounded by an event horizon, the boundary beyond which escape is impossible. But there's another type of black holes, supermassive black holes. These aren't the remnants of dead stars. They're millions or billions of times more massive than our sun, and they lurk at the centers of most large galaxies, including our own. The Milky Way's central black hole, Sagittarius A star, weighs about 4 million times what our sun weighs. That sounds enormous, and it is, but it's tiny compared to some. The galaxy M87, famous for the first ever image of a black hole's event horizon captured in 2019, has a central black hole weighing 6.5 billion solar masses. That's unfathomable. A region of space so massive, so gravitationally dominant, that it holds an entire galaxy in orbit around it. The question that's plagued astronomers for decades is this: how did these supermassive black holes get so big? Black holes can grow by consuming matter that falls into them. Gas, dust, even entire stars can spiral inward, forming a hot, glowing accretion disk before finally crossing the event horizon. But there's a limit to how fast a black hole can grow this way. As matter falls in and heats up, it emits radiation, lots of it, so much that the outward pressure from that radiation pushes against the incoming matter, choking the flow. This creates what's called the Eddington limit, a natural speed limit for black hole growth. If a black hole feeds faster than this limit, the radiation pressure blows away the food supply. It's self-regulating. Given this limit, even if a black hole started at 100 times the mass of our sun, which is already extremely large for a stellar remnant, it would take billions of years to grow to 1 million solar masses. And to reach 1 billion solar masses, that should require 10 billion years or more. But here's the problem. James Webb has found supermassive black holes that already weigh 1 billion solar masses when the universe is less than 1 billion years old. Some exist when the universe is only 700 million years old. They didn't have enough time to grow. Not through normal feeding, not at the Eddington limit. The math doesn't work. And then Webb found something even stranger, an object called LID 568. It's in a dwarf galaxy, a small galaxy, just 1.5 billion years after the Big Bang. When astronomers observed it with both Webb's infrared instruments and the Chandra X-ray Observatory, they detected something that should be impossible. This black hole is feeding at 40 times the Eddington limit. 40 times, not a little bit over, not twice as fast. 40 times faster than physics says it should be able to feed. It's gorging itself, consuming matter at a rate that should create so much radiation pressure that the entire process chokes itself off. But it's not choking. It's thriving. How is this possible? The leading theory is that LID 568 is in the middle of what's called a super Eddington accretion episode. Imagine a black hole sitting in a relatively quiet region of a galaxy. It's feeding slowly, at or below the Eddington limit, growing gradually. And then something happens. Maybe two galaxies collide, disturbing the gas in both. Maybe a massive cloud of cold gas collapses directly onto the black hole from all directions at once. Suddenly, instead of matter spiraling in from a thin disk, it's falling in from every direction simultaneously. The radiation can't push it all away because there's too much of it coming from too many angles. For a brief period, cosmically speaking, the black hole can feed much faster than normal. It can exceed the Eddington limit. It can double or even quadruple its mass in just a few million years. Webb caught LID 568 inches the act, a snapshot of a black hole in the middle of a feeding frenzy. And if this happened to LID 568, it probably happened to countless other black holes in the early universe. Brief episodes of super Eddington accretion, allowing black holes to bulk up much faster than steady, slow feeding would allow. This might explain how supermassive black holes got so big so fast, but it's still a hypothesis. We're still putting the pieces together, and every new observation from Webb brings more puzzles, more questions, more cracks in the edifice of our understanding. Let me tell you about another mystery Webb uncovered. These are called little red dots. When astronomers first started examining Webb's deep field images, they noticed these tiny reddish smudges scattered throughout the frames. At first glance, they look like ordinary distant galaxies. Red because their light has been shifted into the infrared by cosmic expansion. Small because they're far away. Nothing unusual. But when spectroscopic analysis came back, revealing the detailed properties of these objects, astronomers realized these were anything but ordinary. They're compact, extremely luminous, and their characteristics don't match any type of object we've seen in the nearby modern universe. Some of these little red dots appear to be incredibly dense star clusters, places where stars are packed so tightly together that they'd be constantly colliding and merging. In our galaxy, stars are separated by vast distances. Even in dense regions like the core of a globular cluster, stars are light years apart. But in these little red dots, stars seem to be separated by distances comparable to our solar system. That's unfathomably dense, and it creates problems. When stars get that close, they interact gravitationally, they steal mass from each other, they merge. The result should be runaway collisions, creating ever more massive stars, until you end up with a single supermassive star that quickly explodes. But these objects seem stable, at least temporarily. Other little red dots show evidence of extremely massive black holes. And here's where it gets truly strange. The black hole often weighs as much as, or more than, the entire galaxy's worth of stars surrounding it. This is completely inverted from what we see in modern galaxies. In the Milky Way, the central black hole weighs about 4 million solar masses, while the total stellar mass is around 60 billion solar masses. The ratio is roughly 1 to 15,000. The black hole is a tiny fraction of the galaxy's total mass, but in some little red dots, that ratio is 1 to 1, or even greater than 1. The black hole outweighs the galaxy hosting it. This inverts our entire understanding of how galaxies and black holes grow together. The standard model says galaxies form first, building up stars gradually through gas accretion and mergers. As the galaxy grows, some gas funnels toward the center, feeding a growing black hole. Over time, the black hole and the galaxy reach a kind of equilibrium. They grow together, maintaining a relatively constant ratio. The black hole regulates its own growth by heating and blowing away gas that would otherwise fall into it, a process called AGN feedback. This prevents the black hole from getting too big relative to its host galaxy. It's a self-limiting system, or so we thought. Little red dots show this relationship completely flipped. The black hole got huge first. The galaxy is still catching up. Some astronomers think these are transition objects, snapshots of galaxies caught in adolescence, when the central black hole has grown rapidly through super-Eddington accretion, but the surrounding galaxy hasn't yet assembled its full complement of stars. Give these systems a few 100 million years, and maybe they'll look like normal galaxies with appropriately sized black holes. Others think little red dots represent a completely different formation pathway. Maybe some galaxies form black holes first, seeds them early, and then build stars around them later. Maybe in the early universe, before there were many heavy elements, gas could collapse directly into massive black holes without forming stars first. We don't know. And again, that's the point. Webb is showing us that the early universe operated by rules we haven't fully uncovered yet. Over 100 of these little red dots have been identified so far. They appear at multiple distances, multiple epochs, meaning they were a common feature throughout the first billion years of cosmic history. This wasn't a rare fluke. It was standard operating procedure. The early universe was building galaxies in ways we never predicted, couldn't have predicted, because we'd never seen that era before. Hubble couldn't reach back this far. Only Webb can. And what it's revealing is a cosmos that was wilder, more chaotic, more creative than any simulation suggested. Now, let me bring this back to where we started. That grain of sand, that impossibly small patch of sky. James Webb's first deep field image, released in July 2022, showed a region of space smaller than a grain of sand held at arm's length. The observation lasted about 12.5 hours. In that tiny patch, Webb found thousands of galaxies. Later surveys expanded this. The Cosmos Web survey, which I mentioned earlier, covered an area roughly 3 times the size of the full moon as seen from Earth. In that slightly larger but still minuscule region, Webb detected over 800,000 galaxies. 800,000, each one a complete universe in its own right. Each one containing billions or trillions of stars, each one potentially harboring countless worlds. The full sky, the entire celestial sphere surrounding Earth, contains about 41,000 square degrees. If every patch of sky contains the same density of galaxies as these deep field observations suggest, then the total number of galaxies in the observable universe exceeds 2 trillion. 2 trillion galaxies. This number is so large it ceases to have meaning in any intuitive sense. You cannot visualize 2 trillion. You cannot hold it in your mind. It's an abstraction. A symbol of vastness so profound that it should be overwhelming. And yet, here's the strange thing. It's not overwhelming. Or rather, it is overwhelming, but in a way that ultimately feels liberating rather than crushing. Let me explain what I mean. For most of human history, we've been trying to find our place in the cosmos. We started thinking we were the center of everything, the point around which the heavens revolved. That was comforting in a way. We mattered. We were important. The universe was built for us. Then Copernicus and Galileo shattered that illusion. We weren't the center. We were orbiting the sun, not the other way around. That was humbling, but we could still maintain that our sun, our solar system, was special somehow. Maybe we were the only ones. Maybe life, intelligence, consciousness existed nowhere else. We were still unique, even if we weren't central. But then we discovered the Milky Way was full of billions of stars, and then we discovered there were billions of galaxies beyond our own. And now Webb has shown us there are trillions of galaxies, each potentially containing billions of worlds. The odds that we're alone have shrunk to essentially zero. Somewhere out there, in one of those 2 trillion galaxies, on one of the countless billions of planets orbiting one of the innumerable stars, there is almost certainly other life, other intelligence, other consciousness looking up at their own night sky and wondering if they're alone. This should be existentially terrifying. We are not special. We are not central. We are not even particularly rare. Statistically speaking, we are one arrangement of matter among an incomprehensibly vast number of arrangements existing for a cosmically brief moment on a tiny world orbiting an ordinary star in an unremarkable location within one galaxy among trillions. By any objective measure, we do not matter. The universe is vast and ancient and indifferent. It operated for over 13 billion years before Earth even formed. It will continue operating for trillions of years after our sun dies, after our galaxy collides with Andromeda, after every star we can see has exhausted its fuel and gone dark. We are a blip, a flash, cosmically insignificant, and yet, here we are, conscious, aware, capable of understanding all of this. We are an arrangement of atoms that somehow became able to contemplate arrangements of atoms. We are matter that gained the ability to study matter. We are the universe looking at itself and marveling at what it sees. And that capacity, that ability to comprehend cosmic scale, to trace the history of the universe from the Big Bang to the present, to understand how stars form and die and scatter the elements that make up our bodies, that capacity is extraordinary. Perhaps the most extraordinary thing the universe has ever produced. As far as we know, let me put this in perspective. You are made of elements that were forged in the cores of dying stars. The hydrogen in your body was created in the Big Bang itself, 13.8 billion years ago. The carbon, nitrogen, oxygen, calcium, iron, all the heavier elements, they came from stars. Some from massive stars that lived fast and died young in spectacular supernova explosions. Some from white dwarfs that slowly accumulated material from companion stars until they could no longer support themselves and collapsed. Some from the collisions of neutron stars, events so violent they created ripples in space-time itself. All of these processes happened over billions of years. Throughout the history of the cosmos, stars formed, lived, died, and scattered their ashes. Those ashes coalesced into new stars and new planets. And one of those planets happened to be in the right place, at the right distance from its star, with the right mix of elements, and life emerged. And that life evolved, and eventually, after hundreds of millions of years, it produced you. You are the product of 13.8 billion years of cosmic history. Every atom in your body is ancient beyond imagining. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was created in the hearts of stars that lived and died before our sun even existed. You are quite literally made of stardust. This is not a metaphor. This is a scientific fact. And when you die, when your body decomposes, those atoms will return to the earth. They'll be absorbed by plants, by microbes, by other creatures. Eventually, billions of years from now, when our sun expands into a red giant and engulfs the inner planets, even the atoms that once composed you will be scattered back into space. They'll become part of new nebulae, new stars, new worlds, new life, perhaps. The universe recycles everything. So here's the paradox. You are simultaneously insignificant and miraculous. You are one temporary arrangement of atoms among trillions upon trillions of arrangements. You occupy a vanishingly small fraction of space and time. And yet, as far as we know, you might be one of the rarest things in the entire cosmos. Because consciousness, true self-awareness, the ability to look up at the night sky and understand what you're seeing, that might be extraordinarily uncommon. Yes, there are probably trillions of planets, but how many of them have life? How many have complex life? How many have intelligent life? And how many have life that's reached the point where it can build instruments to study the universe itself? We don't know. But the fact that it happened here, on this small world, in this ordinary galaxy, that you exist and can comprehend your own existence, that's astonishing. That's worth marveling at. So when I tell you that James Webb has revealed the true scale of the universe, I'm not just talking about numbers. I'm not just talking about 2 trillion galaxies or 93 billion light years or 280 million years after the Big Bang. I'm talking about perspective, about context, about understanding your place in the grand sweep of cosmic history. You are tiny, you are brief. You are one of billions of humans on one planet, among billions of planets. But you are also connected to everything. The atoms in your body, the light entering your eyes, the thoughts forming in your mind, all of it is part of the same universe that contains those distant galaxies, those ancient black holes, those impossible early structures. You are not separate from the cosmos. You are an expression of it, a way the universe has organized itself to become aware of itself. Let me tell you a story that might help illustrate what I mean. In the 1970s, NASA launched 2 spacecraft, Voyager 1 and Voyager 2. Their primary mission was to explore the outer planets, Jupiter, Saturn, Uranus, Neptune. They succeeded brilliantly, sending back images and data that revolutionized our understanding of these distant worlds. But after completing their planetary encounters, the Voyagers kept going. They're still traveling today, moving away from the sun, heading toward interstellar space. In 1990, when Voyager 1 was about 6 billion kilometers from Earth, the astronomer Carl Sagan convinced NASA to turn the spacecraft's camera around and take one last picture of home. The result is an image called the pale blue dot. In it, Earth appears as a tiny speck, barely a single pixel, suspended in a sunbeam. That's us. That's home. Everything that has ever happened in human history, every war, every love story, every discovery, every triumph and tragedy, all of it took place on that pale blue dot. Carl Sagan wrote about this image, and his words are worth remembering. He said, "Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization. Every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. That perspective, that cosmic humility, is what Webb's discoveries invite us to embrace. Not as a source of despair, but as a source of clarity. Because once you truly understand how vast the universe is, how ancient, how indifferent, it frees you from certain illusions. The illusion that your problems are cosmic in scale, the illusion that the universe owes you anything, the illusion that your existence needs to be validated by forces beyond yourself. None of that is true. The universe is not keeping score, it's not watching. It doesn't care whether you succeed or fail, whether you're happy or miserable, whether you live or die. And that's okay. That's liberating, actually, because it means you get to decide what matters. You get to choose how to spend your brief time here. You get to create your own meaning. Now, I want to talk about something that might seem like a tangent, but I promise it connects time. Specifically, the strange way time works when we observe distant galaxies. When you look at a star in the night sky, you're not seeing it as it is right now. You're seeing it as it was when the light left it. Light travels fast, incredibly fast, but space is so vast that even light takes time to cross it. The nearest star to us, beyond our sun, is Proxima Centauri, about 4.2 light years away. When you see that star, you're seeing light that left it 4.2 years ago. If something happened to that star tomorrow, if it exploded or dimmed or changed in any way, you wouldn't know for another 4 years. The light carrying that information hasn't reached you yet. The farther you look, the farther back in time you're seeing. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. The light reaching your eyes tonight left Andromeda 2.5 million years ago, when early humans were just beginning to use simple stone tools. The light from distant galaxies observed by Webb left those galaxies over 13 billion years ago, when the universe was young, when stars were just beginning to form, when the cosmos was a chaotic, violent place. We're not seeing those galaxies as they are now. We're seeing ghosts, echoes of light from objects that might not even exist anymore. Those ancient stars have long since died. Those galaxies have collided with others, merged, transformed into something unrecognizable. This is what makes Webb a time machine. When it looks at distant galaxies, it's literally looking backward through time. Every distance corresponds to a different era in cosmic history. The nearest galaxies show us what the universe looked like a few billion years ago. The farthest galaxies show us cosmic dawn, the era when the first stars were igniting. By observing galaxies at different distances, at different redshifts, Webb is building a timeline, a movie of cosmic evolution frame by frame. And what that movie is revealing is that the early universe was nothing like we expected. But here's the part that really bends the mind. This is true for your life too. Not metaphorically, literally. When you look at someone across the room, you're seeing them as they were a few nanoseconds ago, the time it took light to travel from them to your eyes. When you see the sun, you're seeing it as it was 8 minutes ago. The sun could have exploded 7 minutes ago and you wouldn't know yet. You'd still see it shining. And when you remember a conversation, an event, a moment from your past, you're not experiencing the present. You're reconstructing something that no longer exists. Your memories are like the light from distant galaxies. They carry information about something that has already ended, something you can observe but never return to. The present moment, the true present, is impossibly thin, vanishingly small. By the time your brain processes sensory input and becomes aware of it, that moment has already passed. You are always living in the recent past. Your consciousness lags behind reality by milliseconds. This is not a flaw, it's just the nature of perception, of awareness, of being a physical system operating under the laws of physics. And yet, despite this limitation. Despite the fact that we're always seeing and experiencing and remembering things that have already happened, we manage to navigate the world. We build relationships. We create. We love. We find meaning. We live. There's something profound in this. Something about acceptance, about working within constraints, about recognizing that you can't change the past, that you can only move forward, that the present is fleeting but also the only thing you ever really have. James Webb has taught us that looking backward is how we understand where we came from. Studying ancient light from distant galaxies tells us how the universe evolved, how structures formed, how we got here. And maybe that's true for our personal lives as well. Understanding where you came from, the experiences that shaped you, the moments that defined you, that's how you make sense of who you are now. Not to dwell on the past, not to get stuck there, but to understand it so you can move forward with clarity. Now I want to share something with you that might change how you think about scale, about size, about what it means for something to be big or small. We tend to think of size in absolute terms. The universe is big. You are small, but size is always relative. Compared to an atom, you are incomprehensibly vast. Your body contains roughly 7 octillion atoms. That's 7 followed by 27 zeros. If each atom were a grain of sand, you would contain more grains than exist on all the beaches on Earth. Compared to an atom, you are a universe unto yourself, a vast collection of particles interacting in precisely coordinated ways that somehow give rise to consciousness, to awareness, to the sense of being you. And compared to the observable universe, you are vanishingly small. But here's the interesting thing. The size ratio between you and an atom is not that different from the size ratio between you and the observable universe. You sit roughly in the middle of the scale of sizes in the cosmos. The smallest meaningful length in physics is the Planck length, about 10 to the negative 35 meters. It's the scale at which quantum effects of gravity become important, where space and time themselves become grainy and uncertain. The size of the observable universe is about 10 to the 27 meters. And you're about 1 to 2 meters tall. Right in the middle, logarithmically speaking. You're as much bigger than the Planck length as the universe is bigger than you. This means something important. It means you're not at the bottom of the cosmic hierarchy. You're not the smallest, most insignificant thing. You're in the middle. You're a bridge between the quantum realm and the cosmic scale. You contain multitudes of atoms, and you're contained within multitudes of stars. You're both container and contained, both vast and tiny, depending on perspective. This is another way of thinking about your place in the cosmos, not as the center, but also not as the irrelevant periphery, as a node in a vast web of scales and structures, each connected to all the others. Let me tell you about something called the cosmic calendar. It's a way of visualizing the age of the universe by compressing all 13.8 billion years into a single year. This was popularized by Carl Sagan in his series Cosmos, and it remains one of the most powerful tools for understanding cosmic timescales. If the Big Bang occurred at the stroke of midnight on January 1st, when does everything else happen? The Milky Way galaxy forms around March 16th. Our solar system doesn't form until September 2nd. Life on Earth emerges in mid-September. For months, for most of the year, there's nothing on Earth but single-celled organisms. The first multicellular life doesn't appear until mid-November. Dinosaurs don't appear until December 25th, Christmas Day, and they reign for about 4 days before going extinct on December 30th. All of human history, from the earliest civilizations to the present day, occurs in the final minute before midnight on December 31st. Think about that. Everything you learned in history class, every empire, every war, every artistic movement, every scientific discovery, all of it happened in the last minute of the cosmic year. Your entire lifespan is a fraction of a second. You are born, you live, and you die in the blink of a cosmic eye. And yet, in that fraction of a second, you can learn about the entire year. You can understand the Big Bang, the formation of galaxies, the evolution of life, the future fate of the universe. You can compress 13.8 billion years of history into your brief awareness. That's extraordinary. But the cosmic calendar also reveals something else. how recent and how fragile we are. Humans have only been around for the last few seconds of the cosmic year. Civilization for a fraction of a second. And yet in that impossibly brief time, we've transformed the planet. We've split the atom, we've walked on the moon, we've built telescopes that can see to the edge of the observable universe. We've decoded the human genome. We've connected billions of people through global communication networks. We've created art, music, literature, philosophy. We've asked questions about meaning and purpose and existence. We've wondered whether we're alone. We've built instruments to search for answers, all in the last second of the cosmic year. If the universe were a person, we would be the last thought they had before falling asleep. And yet, that thought contains everything we are, everything we've ever done, everything we might become. This perspective can be overwhelming. I understand that. It can make your problems seem trivial, your ambitions insignificant, your life meaningless. But I want to offer a different interpretation. Yes, we're recent. Yes, we're brief. But we're also astonishing. The universe spent 13.8 billion years setting the stage, creating stars, forging elements, forming planets, nurturing life, and then, in the last possible moment, it produced us. Conscious observers capable of understanding the whole story. That's not an accident, that's not a footnote, that's the culmination. Or at least one of the culminations. There might be others. There probably are others, scattered among the 2 trillion galaxies. But here, on this world, in this moment, you are the universe's way of knowing itself. Now let me bring this back to James Webb and what it's teaching us about the nature of reality. One of the most profound lessons from Webb's discoveries is this. The universe doesn't care about our models. It doesn't wait for us to give it permission to behave a certain way. It does what it does, and our job is to observe, measure, and try to understand. Before Webb, we had a neat story about how galaxies formed. Slowly, gradually, over hundreds of millions of years. But Webb showed us galaxies forming in a fraction of that time. Does that mean the universe broke its own rules? No. It means our rules were incomplete. We were missing something. Some process, some mechanism, some force that allowed galaxies to assemble faster than we thought possible. This happens all the time in science. We build a model based on the data we have. The model makes predictions. We test those predictions, and sometimes the predictions are wrong. Not because the universe is capricious or malicious, but because our model wasn't complete. It was based on limited information. And when we get new information, better data, deeper observations, we have to revise the model. Sometimes we can patch it, add a new variable, tweak a parameter. Other times we have to throw it out and start over. This is not a failure of science. This is how science works. Models are tools, not truths. They're approximations, useful fictions that help us make sense of reality. But they're not reality itself. Reality is what the universe actually does. And the universe is under no obligation to conform to our expectations. I think there's a life lesson here. You have models too. Mental models about how things should work, how relationships should unfold, how careers should progress, how healing should happen, how change occurs. These models are based on your experiences, your observations, the patterns you've noticed, and they're useful. They help you navigate life, make decisions, predict outcomes. But sometimes reality doesn't match the model. Things don't happen the way you expected. Someone you trusted betrays you. A career path that seemed certain collapses. A healing process that should have taken months takes years. Or the opposite happens. You recover faster than you thought possible. You find love when you'd given up looking. You succeed despite overwhelming odds. When reality diverges from your model, it's tempting to blame reality, to think something has gone wrong, to feel like you're broken or cursed or uniquely unfortunate. But maybe the model was just incomplete. Maybe you were missing a variable. Maybe the universe, or life, or whatever you want to call it, operates by rules you haven't fully discovered yet. This doesn't mean you should abandon all models, all expectations, all attempts to understand. It means you should hold them lightly, use them as guides, not gospel. Be willing to revise them when new evidence comes in. Be willing to admit when you don't know. Be willing to sit with uncertainty, because uncertainty isn't the opposite of knowledge. It's the space where new knowledge can emerge. James Webb is teaching us to be humble, to recognize the limits of our understanding, to approach the universe with curiosity rather than certainty. And I think we could all benefit from bringing that attitude into our daily lives. Not just when we're studying galaxies or black holes, but when we're navigating relationships, careers, health, all the messy, complicated, unpredictable aspects of being human. Uncertainty is uncomfortable. I know that. We crave certainty, control, predictability. But life isn't giving us that. The universe isn't giving us that. And maybe that's okay. Maybe the uncertainty is where the beauty lies. The possibility, the potential for surprise, for growth, for transformation. Let me tell you about another discovery. Webb has made one that speaks to the theme of surprise, of the universe being stranger than we imagined. Webb has been observing what are called gravitational lenses. These occur when a massive object, like a galaxy cluster, sits between us and a more distant galaxy. The cluster's gravity is so strong that it bends the fabric of space-time around it, like a heavy ball sitting on a rubber sheet. Light from the distant galaxy has to travel through that bent space-time, and as a result, it gets deflected, magnified, sometimes split into multiple images. The cluster acts like a cosmic magnifying glass, allowing us to see galaxies that would otherwise be too faint and too distant to detect. Einstein predicted this effect in his general theory of relativity over a century ago, but it wasn't confirmed until much later. And now, with Webb, we're using gravitational lensing as a tool, a natural telescope created by the universe itself. Some of the most distant galaxies Webb has observed are only visible because a massive cluster sits in front of them, magnifying their light by factors of 10, 100, sometimes more. The universe has given us a gift, a way to see farther than our instruments alone would allow. And what we're seeing in these magnified images is, once again, surprising. Galaxies that are smaller, denser, stranger than expected, star formation happening in bursts rather than steady streams. Chemical compositions that don't quite match our models. The more we look, the more we find that doesn't fit. This is exhilarating. At least it should be, because it means we're still learning, we're still discovering, the universe still has secrets to reveal. If everything matched our predictions perfectly, if every observation confirmed what we already thought, that would be boring. It would mean we'd figured everything out, that there was nothing left to explore. But that's not the case, not even close. We've barely scratched the surface. Webb has been operational for just over 2 years, and it's already transformed our understanding of the early universe, of galaxy formation, of black hole growth, and it's expected to operate for at least another 10 years, possibly longer. Imagine what we'll learn in that time. Imagine the discoveries still to come, the surprises, the paradigm shifts, the moments when everything we thought we knew gets turned upside down. This is what makes cosmology, what makes science in general so thrilling. It's not about arriving at final answers. It's about the journey. The process of questioning, observing, testing, revising. It's about being wrong and admitting it and trying again. It's about encountering mystery and leaning into it rather than away from it. And I think there's a parallel here to personal growth, to the work of being human. We're not trying to become perfect, to reach some final state where everything is resolved and understood. We're trying to grow, to evolve, to become more fully ourselves. And that requires encountering mystery, sitting with uncertainty, being willing to be wrong about ourselves and revise our self-understanding. It requires humility, curiosity, and courage. Let me share one more technical detail about Webb that has profound philosophical implications. Webb doesn't just take pictures, it performs spectroscopy, breaking light into its component wavelengths. Every element, every molecule absorbs and emits light at specific wavelengths, creating a unique signature. By analyzing the spectrum of light from a distant galaxy, we can determine what elements are present, how fast the galaxy is moving, how hot its stars are, whether it contains dust or gas, even whether it might harbor planets with atmospheres. Spectroscopy is like reading the universe's chemical fingerprint. And what Webb is finding over and over is that the early universe was chemically enriched much faster than we thought. Remember, after the Big Bang, the only elements that existed were hydrogen, helium, and traces of lithium. Everything else, every element heavier than helium, had to be created inside stars. Carbon, nitrogen, oxygen, silicon, iron, all of it comes from stellar nucleosynthesis or supernova explosions. In the modern universe, we see lots of heavy elements. Our sun is rich in metals, as astronomers call all elements heavier than helium. Our planet is made mostly of heavy elements: iron, silicon, oxygen, carbon. But that's because our sun formed relatively recently, cosmically speaking, about 4.5 billion years ago. It formed from gas that had already been enriched by previous generations of stars. The first stars didn't have that luxury. They formed from pure hydrogen and helium, and those stars had to live and die before the next generation could form. This process takes time. A massive star lives for only a few million years before exploding as a supernova. But then the ejected material has to cool, condense, mix with surrounding gas, and collapse into new stars. We thought this would take hundreds of millions of years, but Webb is finding galaxies at redshift 10, 11, 12, 13, 14, galaxies that existed less than 500 million years after the Big Bang, and they already show evidence of heavy elements in their spectra. Carbon emission lines, oxygen emission lines. These elements shouldn't be there yet, or they should be there in much smaller quantities. But they're not. They're abundant, which means stars were forming, living, and dying much faster in the early universe than our models predicted. The cosmic recycling process was turbocharged. And again, we don't fully understand why. Maybe stars formed more efficiently back then. Maybe they were more massive on average, burning through their fuel faster. Maybe supernova explosions were more effective at dispersing material. We're still figuring it out. But here's what strikes me about all this. The universe found a way. It needed to create heavy elements quickly, and it did. It improvised. It adapted. It didn't follow our neat, orderly timeline. It found shortcuts, workarounds, alternative pathways. The universe is creative, it's resourceful, it's resilient. And maybe that's the deepest lesson Webb is teaching us. The universe is not a machine following a fixed program. It's a dynamic, evolving, self-organizing system that responds to conditions, that finds ways to make complexity happen even when the conditions seem hostile. Stars form in the hearts of collapsing gas clouds, despite magnetic fields and turbulence trying to prevent it. Galaxies assemble despite the expansion of space trying to pull everything apart. Life emerges on planets despite countless threats to its survival. And consciousness arises despite the improbability of neurons organizing themselves into patterns that can reflect on their own existence. At every level, from the quantum to the cosmic, the universe is doing things that seem unlikely, improbable, even impossible by naive estimates. And yet, here we are. Here it all is. The universe exists, and it's filled with structure, complexity, beauty, meaning. Not because it had to be this way, but because the laws of physics, the initial conditions, the random fluctuations, all of it conspired to allow this outcome. Or rather, our existence selects for a universe that allowed this outcome. The anthropic principle, the observation that the universe must be compatible with conscious observers because we are conscious observers. If the constants of nature had been slightly different, if the Big Bang had unfolded differently, if any number of factors had varied even slightly, we wouldn't be here to wonder about it. So in a sense, the universe we observe is necessarily one that permits observation. This can sound circular, tautological, but it's actually profound. It means that your existence, improbable as it is, was made possible by the precise configuration of the universe from its very beginning. The Big Bang created the conditions for stars. Stars created the conditions for planets. Planets created the conditions for life. Life created the conditions for consciousness. And consciousness creates the conditions for understanding. You are the endpoint of a chain of causation stretching back to the origin of everything. And that chain could easily have been broken at any point. If the expansion rate had been slightly faster, matter wouldn't have clumped together. No stars. If the nuclear forces had been slightly weaker, stars wouldn't have been able to fuse hydrogen into helium. No energy source for solar systems. If supernovas didn't disperse heavy elements, there would be no carbon, no chemistry, no life. Every step was necessary. And every step was contingent, uncertain, fragile. You are the beneficiary of 13.8 billion years of cosmic evolution proceeding in exactly the right way to permit your existence. And when I say right, I don't mean morally right or intentionally right. I mean compatible. The universe is compatible with you. You fit. You belong. Not in the sense that you were designed or intended, but in the sense that you are a natural outgrowth of the laws and conditions that govern reality. You are not an accident in the sense of being a mistake. You're an accident in the sense of being one possible outcome among many. But you're also an inevitable outcome given the specific history that unfolded. If we could rewind the universe and let it evolve again, you wouldn't exist. Different quantum fluctuations would lead to different galaxies, different stars, different planets, different evolutionary pathways. But something would exist. Some form of complexity, some arrangement of matter capable of self-reflection. The universe seems predisposed to create complexity, to organize itself into interesting structures, to find ways to violate our expectations and surprise us with its creativity. Now I want to talk about what all of this means for how you live your life, because ultimately, that's what matters. Not the technical details of galaxy formation or black hole accretion, but what these discoveries mean for you, here, now, trying to navigate the challenges of being human. And I think the central insight is this: you are both insignificant and precious. These are not contradictory. They're both true simultaneously. You're insignificant in the sense that the universe doesn't revolve around you, doesn't depend on you, won't notice when you're gone. But you're precious in the sense that you are rare, improbable, a fleeting arrangement of matter that briefly gained the ability to experience wonder, love, curiosity, joy. You are cosmically unimportant and humanly invaluable, and learning to hold both of these truths at the same time is what cosmic humility is all about. Too much focus on insignificance leads to nihilism, to the sense that nothing matters, that all effort is futile, that we're just meaningless specks in an indifferent cosmos. Too much focus on preciousness leads to narcissism, to the sense that we're the center of everything, that our feelings and desires and experiences are supremely important, that the universe owes us something. The balance is recognizing that we matter enormously to ourselves and to the people we care about, but not to the cosmos. Our significance is local, not universal. And that's fine. It has to be fine, because it's all we have. Think about the people you love, your family, your friends, your partner if you have one. Do they matter cosmically? No. The universe would continue exactly as before if they ceased to exist. But do they matter to you? Of course, profoundly. Their existence shapes your life in ways that are irreplaceable and irreplicable. The same is true in reverse. You matter to them, not because of some cosmic designation, not because the universe says you should, but because of the relationships you've built, the experiences you've shared, the ways your lives have become entangled. Meaning is local. It emerges from connection, from proximity, from shared context. And that's enough. It's more than enough. It's everything. James Webb has given us the gift of perspective. It's shown us how vast the universe is, how ancient, how full of galaxies and stars and worlds beyond counting. And in doing so, it's shown us how small we are, how recent, how fragile. But it's also shown us how remarkable we are. Because we built Webb. We designed it, tested it, launched it, positioned it 1 million miles from Earth. We wrote the software to control it, to point it at the right targets, to collect and process the data. We developed the theoretical frameworks to interpret what we're seeing. We connected the observations to our understanding of physics, of chemistry, of the history of the cosmos. All of this required intelligence, creativity, persistence, collaboration. Thousands of people working together over decades to make this mission possible. And it succeeded. It's working. It's sending back images and data that are revolutionizing our understanding of the universe. That's extraordinary. That's what humans can do when we focus our collective effort on something larger than ourselves. And this is true in other domains as well. We've cured diseases, we've written symphonies, we've built cities, we've explored the deepest oceans and the highest mountains. We've painted masterpieces, we've written poems that capture the ineffable. We've developed philosophical systems to make sense of existence. We've created technologies that connect us across vast distances. We've sent humans to the moon and robots to Mars. We've split the atom and decoded the genome. We've done all of this despite being tiny, fragile, short-lived creatures on a small planet in an ordinary galaxy. We've done it because we're curious, because we're creative, because we're capable of working together towards shared goals. That capability is worth celebrating, it's worth honoring, it's worth protecting. But here's the thing, all of those achievements, impressive as they are also cosmically insignificant. The universe doesn't care that we went to the moon. It doesn't care about Shakespeare or Mozart or Einstein. It doesn't care about democracy or human rights or justice. These things matter to us. They matter profoundly. They shape our societies, our values, our sense of what it means to live a good life, but they don't matter cosmically. And recognizing that is liberating, because it means we get to decide what matters. We get to create our own values, our own meanings, our own purposes. We're not beholden to some cosmic authority telling us how to live. We're free, frighteningly free. And with that freedom comes responsibility. The responsibility to choose wisely, to live intentionally, to treat each other with kindness and respect, to build a world that reflects our highest ideals rather than our basest impulses. Let me tell you something practical now, something you can actually do with all this information. Tonight, or tomorrow night, or the next clear evening, go outside. Find a dark place if you can, away from city lights. Let your eyes adjust to the darkness. This takes about 20 minutes, so be patient. And then look up, really look. Don't just glance at the sky. Spend time with it. Find the Milky Way if you can see it. That faint band of light stretching across the sky. That's our galaxy seen from inside. The combined light of billions of stars too distant to resolve individually. Notice how some stars are brighter than others. Notice the colors if you can see them. Some stars are blue-white, burning hot. Others are orange-red, cooler. Find a constellation if you know any. Orion is easy to spot in winter. With his belt of 3 stars, the Big Dipper is visible year-round in the northern hemisphere. And as you're looking, remember what you're seeing. Every point of light is a sun. Many of them have planets. Some of those planets might harbor life. The light entering your eyes left those stars years, decades, centuries ago. It's been traveling through space all that time, and it's arriving right now, right here, to meet your eye. You're intercepting ancient light. You're witnessing the past. And in doing so, you're participating in one of the most human activities there is, looking up, wondering, trying to make sense of the cosmos. Humans have been doing this for hundreds of thousands of years. Long before we had telescopes or cameras or an understanding of what stars actually are, we looked up and wondered. We told stories about the patterns we saw. We use the stars to navigate, to mark the seasons, to locate ourselves in space and time. The night sky was our first map, our first calendar, our first connection to something larger than ourselves. And even now, with all our scientific understanding, with all our instruments and theories and data, the night sky still moves us. It still fills us with awe. It still reminds us of our place in the universe. That sense of awe, that feeling of wonder, that's not something to dismiss or rationalize away. It's something to cultivate. Because wonder is the bridge between knowledge and meaning. Knowledge tells us what the stars are. Massive spheres of plasma undergoing nuclear fusion, converting hydrogen into helium and releasing energy in the process. But wonder asks, what does it mean that we can know this? What does it mean that we, briefly conscious arrangements of stardust, can look up at other distant arrangements of stardust and understand their nature? Wonder transforms facts into significance. It transforms data into wisdom. It transforms the mechanical into the meaningful. So when you look up at the night sky, let yourself feel small. Let yourself feel the weight of cosmic scale, the vastness of space and time, but also let yourself feel connected. Connected to the universe that made you. Connected to the atoms in your body that were forged in stars. Connected to the long chain of causation that stretches from the Big Bang to this present moment. You are not separate from the cosmos. You are part of it, an expression of it, a way it has organized itself to become aware of itself. And that awareness, that consciousness, that capacity for wonder is perhaps the most remarkable thing the universe has ever done, as far as we know. Now, I want to address something that might be troubling you. You might be thinking, if I'm so small, if my life is so brief, if the universe is so vast and indifferent, then what's the point? Why should I bother? Why should I try to achieve anything, build anything, love anyone if it all amounts to nothing in the grand scheme of things? This is a fair question. It's the question at the heart of existentialism, of much of 20th century philosophy, and there are different answers to it. Some people find meaning in religion, in the belief that there is a cosmic significance to their lives, that their actions matter to a divine being, that there's an afterlife where true justice and fulfillment await. I'm not going to argue against that. If it works for you, if it gives your life meaning and helps you treat others with compassion, then it's valuable. But even if you don't believe in a cosmic significance, even if you accept that the universe is indifferent, that your life is brief and local and ultimately forgotten by the cosmos, you can still find meaning. In fact, you have to create it. Because meaning isn't something you discover, like a treasure hidden in the world waiting to be found. Meaning is something you generate through your choices, your actions, your relationships, your attention. You make something meaningful by caring about it, by investing time and energy into it, by treating it as though it matters. And in doing so, you make it matter, not cosmically, but to you. And that's enough. Here's an analogy. Think about a game. Chess, for example. The rules of chess are arbitrary. They were invented by humans. The pieces could have moved differently. The board could have been a different size. None of it matters outside the context of the game. And yet, when you're playing chess, it matters deeply. Which moves you make, whether you win or lose. These things matter within the context of the game. The meaning is local, confined to that space and time, but it's real. You experience it as real. The same is true for life. The rules are arbitrary in some sense. You didn't choose to be born. You didn't choose your genetics, your family, your culture, the historical moment you live in. But given that you are here, given that you are playing the game of life, your moves matter. Your choices have consequences. Not cosmic consequences, but human consequences. You can make someone's day better or worse. You can create beauty or destroy it. You can alleviate suffering or cause it. These choices matter enormously within the context of human life, even if they don't matter to the universe at large. So the answer to nihilism isn't to find some cosmic justification for your existence. It's to recognize that cosmic justification is unnecessary. You don't need the universe to validate you. You don't need your life to echo through eternity. You just need to live it well, according to your own values, in a way that brings you satisfaction and fulfillment and minimizes the harm you cause to others. That's enough. It's more than enough. It's everything. And James Webb, strange as it might sound, supports this view. Because what Webb is showing us is that the universe is vast and ancient and indifferent. It's not hostile. It's not malicious. It's just indifferent. It doesn't care about you, but it also doesn't care about anything else. It doesn't care about galaxies or black holes or stars. These things simply are. They exist, they interact, they evolve according to physical laws. And you are part of that same process. You exist, you interact, you evolve, and within the brief window of your existence, you have the capacity to experience things, to feel things, to care about things. That capacity is the foundation of all meaning. Let me share a story with you, a personal one. There was a time in my life when I struggled with these questions deeply. I was young, maybe in my late 20s, and I just learned about the eventual heat death of the universe. The idea that trillions of years from now, all the stars will burn out, all the black holes will evaporate through Hawking radiation, and the universe will be a cold, dark, empty void. Nothing will remain. No light, no energy, no structure, no possibility of life or thought or experience. Just an infinite expanse of near absolute zero temperature with occasional random quantum fluctuations that lead nowhere. That was the eventual fate of everything. And it devastated me because I thought, what's the point of anything if this is where it all ends? What's the point of building civilizations, creating art, falling in love, if it all ultimately leads to cold nothingness? Every achievement, every relationship, every moment of joy, all of it would be erased as though it never happened. I spent weeks in a kind of existential despair, and then, gradually, I realized something. The heat death of the universe is trillions of years away. Trillions, with a T. That's an incomprehensibly long time. Long enough for countless generations to live and love and create. Long enough for civilizations to rise and fall thousands of times over. Long enough for biological evolution to produce species we can't even imagine. Long enough for intelligence to spread throughout the galaxy, perhaps throughout the cosmos. Long enough for more experiences, more stories, more moments of consciousness than I could possibly conceive. Yes, it all ends eventually. But the journey is so long, so rich, so full of possibility, that focusing on the destination misses the point entirely. The point is the journey, the lived experience, the billions of years of complexity and beauty and meaning that unfold before the final silence. And even that final silence, that ultimate ending, isn't really an ending. It's just a state. A state where nothing happens because there's no energy left for anything to happen. But it's not sad or tragic. It's just what is. The universe doesn't mourn its own end. It doesn't regret. It doesn't feel loss. Those are human emotions, and we project them onto cosmic processes that don't share them. So I stopped worrying about the heat death. I stopped needing the universe to be eternal or meaningful in some grand sense. I focused instead on what's here, now, in this brief window of time when stars are burning, planets are orbiting, life is flourishing, consciousness is emerging. This is the golden age of the universe. We're living in the era when complexity is possible, when structure can form, when experiences can happen. And that's enough. That's more than enough. That's a gift beyond measure. And the appropriate response to that gift is not despair. It's gratitude. Not gratitude to someone or something necessarily, but just gratitude as a state of being. An appreciation for the improbable fact of your existence, for the brief window of awareness you've been granted, for the ability to see and feel and think and love. This is what James Webb is ultimately offering us. Not answers, but perspective. Not certainty, but wonder. Not cosmic validation, but cosmic context. It's showing us where we come from, how we fit into the larger story, what the universe was doing for billions of years before we arrived. And in doing so, it's giving us a clearer sense of who we are. We are latecomers. We are recent. We are the products of a long, complex process that began with the Big Bang and is still unfolding. We are stardust, organized in such a way that it can contemplate stardust. We are the universe's way of knowing itself, of experiencing itself, of marveling at itself, and that's extraordinary. That's worth celebrating. That's worth protecting and nurturing and passing on to future generations. So what do you do with all this? How do you live differently, knowing what you now know about the scale of the universe, the age of the cosmos, the improbability of your existence? I think there are a few practical implications. First, hold your problems more lightly. Not because they're not real or not important, but because they're not cosmic. When you're stressed about work, about money, about relationships, about your health, remember that these concerns, valid as they are, exist on a human scale. They're not going to echo through the ages. They're not going to be remembered by the universe, and that's okay. Deal with them, address them, take them seriously, but don't let them consume you. Don't let them define your entire existence. There's more to life than solving problems. There's also experiencing beauty, feeling connected, being present, appreciating the improbable fact that you're here at all. We've cured diseases. We've extended human lifespan. We've mapped the human genome. We've sent machines to other planets and probes beyond the edge of the solar system. And now, with James Webb, we've built an instrument that can look almost all the way back to the beginning of time itself. Not because we needed to, not because it makes survival easier, but because we wanted to know, because curiosity is one of the most fundamental forces driving our species. That might be the most important thing to understand about Webb. It isn't just a telescope, it's a statement, a declaration that a small, fragile species on a tiny planet can still ask the biggest questions imaginable. That even though the universe doesn't care about us, we care deeply about understanding it, and that care has consequences. It leads to knowledge, perspective, wisdom. James Webb didn't just reveal more galaxies, it revealed how wrong we were about certainty. It showed us that the early universe was faster, denser, brighter, more chaotic than we imagined. That galaxies formed too early. Black holes grew too fast. Heavy elements appeared too soon. The universe didn't ease into complexity, it rushed headlong into it. And that should tell us something important. Complexity doesn't wait for perfect conditions. It emerges wherever it can. Life doesn't require a gentle universe. Consciousness doesn't require a quiet one. Meaning doesn't require permanence. The universe is violent, expanding, indifferent, and yet, somehow, it produces beauty, structure, awareness, again and again. So when you hear that the universe is unimaginably vast, don't hear it as a dismissal of your importance. Hear it as context. You are not less meaningful because the universe is large. You are meaningful because within that vastness, you exist at all and you can understand it. That is not nothing. The universe is vast, beyond comprehension. 2 trillion galaxies, 93 billion light years across. And yet, in all that space, in all that time, the universe produced a species capable of asking, what is this? How did it begin? What is our place in it? James Webb didn't just show us how big the universe is, it showed us how rare understanding might be. And maybe that's the true scale we need to reckon with.